for being here, and thank you for inviting me. And so today, in the first part of this seminar, we're going to talk about operads and how a formalism of trees can be used to encode what operads are. Before starting, I want to take just 1 minute to say a few words about the day of today, which is the 8th of March. So it's the International Women's Day, and it's a day of strike. Many women strike from work. Many women, it's also a social strike where women strike from care work that they provide without being paid or without having to. And yes, I think it's a good moment for us, for everyone, to just to listen to other women which are engaged in actions to bring gender equality in social and workplaces, and equality of salaries and of representations. And yeah, so I thought it was worth mentioning this. And yeah, and this being said, we can talk about infinity operads actually in the first part. So we will start with some motivation and some intuition before giving the definitions. So the idea behind operads is that an operad should be thought of as an abstraction of families of composable operations, so family of operations having multiple inputs and one output, together with a specified composition law that prescribes how to compose these formal operations. And yeah, and these composition laws should satisfy some axioms, the usual axioms of associativity and unitality. So this is the idea we need to have behind what an operad is. And maybe to start building some generalizations above something that we already know, we can think about a representation theory in general. So okay, so we can consider an associative algebra A. And what is a representation of an associative algebra? It is a morphism of algebra from A to the algebra of endomorphism of a vector space. Say that we are considering algebras in vector spaces. What does this mean? Well, that the algebraic structure on A then becomes an actual algebraic structure on V. Okay, so the abstract operation that we have in A then transfer to V to be concrete operations on V. What is the limit of such formalism, say, is that we're modeling operations with only one input and one output, basically, because we are landing in on to V, from V to V. So if we want to model operations with several inputs and one output, we can switch to multi-representation theory. So first of all, we should substitute the algebra on the right, which we understand quite well, with no longer the algebra of linear maps from V to V, but the algebra, but the collection of multilinear maps. So morphisms, linear morphisms from the tensor product of V with itself and times to V, and the collection of such. So the idea behind this is that we should now look at the algebraic structure that this collection of multi operations on V has, in order to then abstract the defining properties of this collection and to give them a general notion of operad that we could place on the right. And okay, so what kind of algebraic structure do the collection of multilinear operations on V has? First of all, for any natural number, we have a vector space which is given by linear functions from V tensor itself n times to V. Okay, so multilinear operations with n inputs and one output. And then we have partial composition maps. What do I mean by this? Well, I mean that if we have f taking as input n variables, and returning one output. And then we have G, which takes in input m variables and then returns again one output of V. Then we can compose F and G. However, there is not one way to compose F and G, because F has several inputs. So in particular, there would be n ways to compose F and G, to compose F with G. These n ways are determined by where we decide to plug the output given by G. So it is for this reason that we can point out that the collection of these multilinear operations that I called NV has this partial composition map. Okay, and so here I showed you, for example, the I composition of F with G. Okay, so here is the first time that I'm introducing trees. So just intuitively, we should think about an operation having n inputs and one output as a tree with n leaves, so n external edges, one root, so the output, and then the vertex is the operation. Okay, it's what taking the inputs return the outputs, and then composing F with G on the I variable of F corresponds precisely to basically identifying the output of G with the I input of F. So grafting, we say these two trees one on top of the other, and then considering the compose operation. Okay, so we have spaces of operations, we have composition laws. What also do we have? Well, we have an action of the symmetric group and elements on the nth space of operations given by the permutation of variables. And okay, so this is the data, and actually we also have another data. We have a canonical element in array T1, which will just be the identity of V. And then all of this data satisfies relations, some axioms. So first of all, composition is associative, but of course we need to formulate the formulation of associativity is a bit more involved, because there is not only one way to compose things, and we need to take into account where the inputs move whenever we move the parentheses. So yeah, here is an example of associativity that we require, and above the example you can see how it can be drawn using trees.
Just have a question.
Yes.
I mean, why would
Thank you.
You're pointing out that anyway, like there's more than two, not bilinear but multilinear. This question arises where to plug in the other tree. Why don't we take? Why do we focus on composing two trees and not at once, like n+1 trees or something like that?
This is definitely possible, and the two definitions are equivalent. So here I decided to give the definition of operads by means of what are called partial compositions. But then there is another definition which basically prescribes, instead of this circ I that go from n tensor n to n plus n minus 1. There are total composition maps, as we say, that will be of the form. We have a tree with n inputs, and then for every input we choose other operations that we want to plug in. So here we will put n1 tensor n and then we will land into, well, the sum of the inputs here. So m1 plus mn. So in this case, we will have, say, from a ternary operation and 3 binary operations, we will get an operation with 6 inputs, which basically composes everything that we did. And these two definitions are exactly equivalent. So yeah, and but then of course, yeah, this total composition should satisfy the same axioms in some sense, and you can pass from one part, from say the partial composition to the total, by iterating the composition by means of associativity, and on the other way you use the identity. So you use the trivial operation, say. But yeah, that's definitely possible. Okay, so we have associativity of this partial composition. We have unitality. So we want that whenever we compose with identity, either after or before taking the elements, we get the same operation. And then all these operations should be, the composition of all these operations should be equivariant, so should respect the action of permutation of variables. Okay, so we quite have all the algebraic structure we need to give a more general definition. So what is an operative vector spaces? Well, it's precisely this. So it's a collection of vector spaces indexed by natural numbers. Pn has to be thought of as the vector space of n-ary operations of P, of formal n-ary operations of P, together with partial composition maps, symmetric group action, unit element, plus axioms. Yes?
Sorry, can I ask you to spell out in a very simple case what the equivalence?
Yes, it would be something like this. So for any so for any sigma in Sn, we would have a sigma star from Pn to Pn. And basically what we want is a commutative diagram of the form Pn tensor Pn, tensor I, Pn plus n minus 1. And here we should have sigma star tensor tau star, Pn tensor Pn. Here we will no longer compose along I, but we will compose along sigma of I, because we have permuted all the inputs.
Sigma means you have both sigma and
sigma is a permutation in Sn, and tau, tau is a permutation in Sm.
Okay.
So and you have this formal action of the. So here we should do O of sigma I, and then here you should put an appropriate permutation obtained from sigma and tau, such that you can make sense of permuting the variables in n and m. It can be constructed quite explicitly, and you require that this diagram commutes.
Okay, so the idea is that if you permutate the inputs, you get permuted outputs. No, that's the commutativity. Right?
Well, this means that, kind of. This means that if you compose operations, you get another, because you get another operation, there is only one output, so you cannot really permute the output. But the composition, So if you compose two multi-operations, you get another multi-operation, and you have a certain permutation. If this permutation is obtained by two separate permutations on n and on m, then you should be able to first act on the single operations and then compose. Okay, we can form a category, of course.
Sorry, this permutation also depends on I, right? The sigma star.
The sigma tau also depends on I. Yeah, for sure. Yeah, thank you. In the case of total composition, no, it will no longer depend. Yeah, definitely. Okay. Okay, we want to form a category. What is a morphism of operands? It will be a map. It will be a collection of maps of vector spaces from Pn to Qn, which commute with composition, which send unit to unit, and which are equivariant, again, with respect to this action of the symmetric group. Sanity check, yeah?
What should I think of this Pn? Should it just be like for any field the standard k to the n, or do you Say like n might be also an like it should have dimension n, or what is Pn?
So Pn, no, really Pn will be just the space. So n only denotes with the fact that your formal operations should have n inputs. So you should think of Pn as a space, a vector space made by some collection of formal operations having
the same arity also.
Exactly, having the same arity, yeah. And
the arity is n, or
and the arity is n, yeah,
okay.
Indeed. So in particular, in the example of before, NVN is really, what is NVN? Well, NVN is precisely, these are concrete operations on V having n inputs and returning one output. So these are really operations on V, and then you abstract and you say, okay, just a collection of vector spaces indexed by n with some axioms, it's an operand. So it's, but we will see some, I hope, insightful examples. But this is just a sanity check because we started from representation theory, from algebras, etc. So we want to check that indeed operads do generalize algebras at least. So we don't have a theory completely different. And well, you can see that whenever you have an associative algebra, it can be turned into an operad by setting the algebra in arity 1, and then the partial composition prescribes that you should go from an operation of arity 1, an operation of arity 1 to an operation of arity 1 plus 1 minus 1, so 1, and this is the multiplication. So yes.
Is it also possible to go the other way around? If you have an operand, you take the degree 1 part.
Yes, indeed. Yeah. Yes. So if you only consider the arity 1 part, it will be precisely an algebra. Yes. Okay. So this only sanity check, and then let's go further. Okay. Representation theory. Again, it was kind of the motivation in the beginning. So we have an algebra. We can represent it as concrete operations on a vector space V. Yeah.
Sorry. In the previous example of the algebra, then okay, this for me formally makes sense, but then PA of 1 is A. Are we thinking of each object of or any element of A as an operation of like acting by multiplication? Or how do we then interpret PA of 1 equals A?
I mean, okay, yeah, that's a good point. So the point is that for any operad, the space of arity 1 is always an algebra, so you should have more this idea in mind. Okay. But I think you can use a regular representation, which is just what? Okay. I think maybe the regular representation would be just multiplication. Yeah, indeed. Yeah, exactly.
Yeah, okay. Yeah, that makes sense.
Yeah. Thank you. And okay, so what is a P-algebra? A P-algebra is a representation of the operad P. So what does it mean? It is a morphism of operads from P to NV. So what does it mean? It means that any formal operation having n inputs in P really becomes a multilinear operation of n inputs on V. And then, of course, again, axioms ensuring that everything is coherent composition. And yeah. So concretely, any F in Pn, so any element in Pn, will give a multilinear map from V tensor n to V. Okay. Okay, I gave you the definition of operad in vector spaces, but actually the only properties that I use of the category of vector spaces is that it has a tensor product. This tensor product is symmetric because I needed the Sn action, and that tensoring with an object has a right adjoint, so the inner home, and this was in order to define algebras. So we call any such category a closed symmetric monoidal category. And in particular, we can define operads in P-algebras for any symmetric monoidal category V. And the definition really goes the same. We just replace vector space, object in vec with object in V, and linear map with morphism in V. Why is this interesting? Well, it is interesting because then we can consider V being chain complexes, vector spaces, yeah, but also sets, topological spaces, or the combinatorial counterpart, simplicial sets, for example. Notice that between amongst these two examples, there is a very important difference. So the ones on the right, on the left, are Cartesian, and the one on the other side are not. So being Cartesian means that the tensor product is really the Cartesian product, so it's a limit. While being non-Cartesian, it means that the tensor product is different from the product. And this will turn out to make an enormous difference when then we pass to the world of homotopy theory, which we will do at some point. But I wanted to bring you an example of why operads are useful, and this is also kind of an historical example because it is how the notion of operad arose back in the 70s. So the point is that operads can be useful to describe algebraic structures which are a bit more exotic than the usual ones that we know, or where, for example, the usual axioms of associativity of the multiplications do not hold strictly. So, for example, for any symmetric monoidal category, we can define what an associative or commutative algebra in V is. Consider the category of topological space. Then a topological monoid is a topological space with a continuous map from x times x in x, a fixed point in x, such that this multiplication is associative and unital. Example, a Lie group. Okay, but actually there are topological spaces which have some algebraic structure which does not quite fit in this very rigid framework. Example, the loop space of a topological space. So consider X a topological space. We can form and the fixed point X is 0 in X. Then we can consider the loop space on X, which I denoted omega X. So what it is, it's the space of continuous maps from the sphere to X, sending a fixed point in the sphere to X is 0, or it's the space of loops in X starting and ending at X 0. Okay, so there is an obvious operation that we can do on loops. We can concatenate them. Okay, so if we have two loops, gamma and psi, then we can consider another loop, which is gamma concatenated with psi from 0, 1 to X. And what does it do? But in the first half of time, it will do psi, and in the second half of the time, it will do gamma. Okay, that's great. It sounds like an operation, like a multiplication. The problem is that it is not associative because, well, when we parenthesize the things in these two different ways, well, the parametrization of the interval is different. So these loops will have the same support, but will not be the same functions on the interval. So this is the point. Okay, this is sad because it was a nice operation, but we observe actually there is an homotopy between the two different ways of parenthesizing the concatenation of two curves. And yeah, this homotopy can be seen as a map from the square to X, starting and ending at the two elements that we want. Okay, so how can we encode this algebraic data? Oh no, I did another one. I did another one. Okay, again, so, I mean, we can go farther with this reasoning. What if we want to concatenate 4 loops? So in which ways and in how many ways these concatenations fail to be associative? Okay, there are homotopies, and actually we see that there is a homotopy between the homotopy linking the various way to associate these loops. Okay, end of the story. Well, we cannot say that the loop space is an algebra because it's not strictly associative, but we can say that it is an algebra over an operad. And this operad is what is called the little cubes operad. So the idea is that the space here, it's a topological space. The space of n-ary operations are the rectilinear embeddings of the disjoint union of n intervals in I. So in particular, for example, C12, so the space of binary operations are just all the possible parametrization that you can have to concatenate two loops. Okay, you can say I'm being constant whenever the interval is black, and then I do the first loop on the first interval 1, and then I do the second loop on the second interval 2. And it is an operad because basically you can plug the embeddings one into the other, and you get this composition. Well, and the proposition, the result is that omega x is indeed an algebra over the little cubes operad. Why? Because this operad basically takes into account all the possible ways I have to parameterize a concatenation. And okay, why is this nice? I mean, this is already nice because we can actually have a control on the algebraic structure of a loop space. But moreover, there is this very important theorem, which is called May recognition principle, which tells us that actually, if we have a topological space, which is group-like, okay, so whose pi 0 has a group structure and pi 1 is abelian, then it is an algebra over the little cube operads if and only if it is homotopy equivalent to the loop space of a topological space. And this is quite a result, because then you have kind of informations about homotopy groups of Y, and yeah. And you can, of course, generalize this to every n, but we're not going to do this. Okay, so this was a bit of motivation about why operads are interesting. And I want to do yet another generalization. So far, I gave you the notion of what an operad is. Now, what if we allow ourselves to label the inputs? So basically, we say that every input, so basically we assign to input elements of an operation a certain type, and we say, or color, and we say that we can compose operations which only end or begin with compatible colors or type. Well, this leads to the notion of colored operads. So again, we take a symmetric monoidal category, chain complexes or topological spaces or whatever. So what is a colored operad in B? Well, it's the data of a set, a class of colors. This means a set of labels that we want of types that the inputs can have. And then for any list of colors, C1, C, and C, we want an object of B, which now represents not all formal n-ary operations, but n-ary operations which can take as inputs element of type C1, C2, C3 in this case, and return as output an element of type C. So we are being more, we're adding a bit of structure. And then there is an analogous composition laws which prescribes that we can only compose those compatible operations. Okay, and then it goes all the same. We want identity elements and actions and everything. Okay, so this is the notion of colored operad. And
so,
yeah.
Elements of C should be seen imagined as data types.
Yeah, you can also like as prescribing what a certain operation, what type of element a certain operation can take in a certain position. So you can say that an operation, yeah. So you can think of them as like type of the elements you can plug in. So you say I cannot put all elements in this first variable. I can just put elements of type C1. Yes?
This is probably a silly question, but is an algebra or some colored operands?
Yes, yeah, indeed. And it's, yeah. Okay, maybe an example. Again, we start with a sanity check. So first, we saw that uncolored operas generalize algebras, okay? What are categories? Categories are like multicolor algebras, okay? Are colored algebras. We allow, we prescribe the elements of a certain type. Okay, and okay, so it makes sense that colored operas should generalize categories, and it is indeed the case, because if we have a category C, then we can create a colored opera whose colors are precisely the objects of C, and then, well, operations don't have multi-inputs, but just have one input and one output, and are the morphisms in C. And this is fully faithful. And again, if you restrict to the spaces of unary operations, you obtain a category. So there is an adjunction. And the composition law is precisely that of C. But we can do more. We can, for example, colored operas also encode, also contain, so there is a fully faithful embedding of categories. The category of symmetric monoidal categories with lax functors between them. So what does it mean? Well, if I have C, a category with a tensor product, okay, a symmetric monoidal category, I should have called the V probably, but okay. Then we can form another operad, which is no longer that, because that doesn't remember of the tensor product structure on C, but we still take colors as objects, as the objects of C, and then we say that morphisms from C1 Cn to D are morphisms in C from C1 tensor Cn to C. So this is we can think of this as the representable opera. So these things are really represented by one object in our category. Okay. Okay. So this is more or less what I wanted to say about operas. And now I would like to introduce the formalism of trees. The formalism of trees, and see how this is very useful to encode functorially the properties that we demand of an operad, and also to say something more. So first of all, what is a tree? A tree is what you expect. So it's I've been drawing them. No, this is the wrong side of the board. Anyway, so a tree is the data of a set of edges. Is the data of a set of edges, a set of vertices. I mean, this is the formal definition, but then we look at the pictures because it's much more intuitive. So a tree has vertices as inner edges. So inner edges are those between two vertices, and have leaves and everything. Okay, so here, this is an example of a tree. Okay, and okay, why are trees so important? So trees will be kind of like the shapes of the operations of an operad. But to start, we can see that any tree generates a colored operad, where the colors are precisely the edges of T, so all the arrows, and the operations are freely generated by the vertices. What do I mean by freely generated by the vertices? Well, any vertex of the tree represents an operation, having as input the input edges, and as output the output edge. So any vertex is an operation. And then, I mean, of course, we also need to have composition of things, and composition of operations correspond to the subtree generated by the appropriate vertices. So in particular, here we can see that we can compose V and W in order to have a map from ADD to R. And we forget about the edge C, which is along which we composed. Okay. And okay, just some terminology, because I will use it very often. So we will say that a tree with n leaves, only one vertex and a root, is an n corolla. I say D because then, of course, there are several n corollas, depending on how you label the leaves. Eta is the tree with no vertices. It corresponds to the terminal category, to the category with just one object and the identity. And these are linear trees. Okay. Yeah, which correspond to simplices to the category associated to the poset of n Okay, and I already give you some terminology, right? So we call inner edges things like this. The leaves are the more external things of the tree, are the more external edges of the tree, which do not come from an input, and then we have the root. Okay. So now what we want to do is use these trees to really encode operads and what they are, the defining properties, etc., in a functorial way. So until now, up to now, we gave the definition of operad by prescribing some structure maps, so the composition maps, and then we wanted associativity, unitality, etc. Well, what we say is that actually it's possible to construct a category omega, a category, such that operads can be embedded into functors out of this category. And okay, that's a bit of an anticipation. Okay, so now we construct a category of trees. So objects are trees, as I defined before, and morphisms between trees will be morphisms between the operads they generate. So in particular, if you consider the tree T here and the tree S here, we see that there is actually a unique morphism from T to S, because the vertex B is a ternary operation in T, so it needs to be sent to a ternary operation in S, and there is only one such operation. And then W is a binary operation. So in principle, we could send it to two places. But then here, these two operations are composable, right? Because the output of V coincides with one of the inputs of W. So the operations in the codomain need to be composable as well. And so we have only one morphism between them. Okay. And
sorry, just
yes,
for clarity, the tree so the operator that is generated by a tree, it will mostly be zero, or not?
So the operations, the spaces of the sets of operation either will be empty or a point. Yes.
Empty,
yeah, or zero and okay. Yeah, indeed.
Okay.
Yes. Okay. So really, we are defining a category strictly linked to what operads are, but given that this is a more combinatorial framework in some sense, we can actually characterize these maps in a much more elementary way, and also very much more insightful. So there is a proposition saying that morphisms in omega are generated not freely by I said three classes of maps because I don't count as morphisms, but therefore classes of maps. So what we call inner faces, outer faces, and degeneracies. So an inner face basically consists, so I have a morphism from S to T, and it is an inner face whenever I can obtain the domain by contracting some inner edge of the codomain. So it's a contraction of inner edges, but then we put the arrow on the other side. Okay, so this is this. Then we have outer faces, and this is just sub-tree inclusions. And finally, we have degeneracies. Degeneracies consist in chopping off a unary vertex and replacing it with just an edge. And then isomorphisms. So the automorphisms, for example, of an n corolla will be the symmetric group on elements. Say. Okay, so these are the thing. So again, I would like to stress that why should trees be related to operads? Well, because an operation of an uncolored operad, say, a colored one, is represented by an n corolla, and then the composition of operations corresponds to this operation of grafting trees one on top of the other. So we identify the root of one with the input of the other. And this, when we forget what's inside, so when we contract an inner edge, so that's an inner face, we get our composition. Okay? Yes. And indeed, before I said a tree generates an operad, and this operad is freely generated by its vertices. Okay? This statement has a precise counterpart inside omega. In what sense? In the sense that any tree can be obtained as a push out, so as a gluing of its subtrees. So again, I'm repeating over and over again the same thing. No? Like a tree is determined by its corollas, and we can obtain it by grafting them one on top of the others. Observe that this push out is done along external, that this push out helps external faces, so subtrees inclusions. This will be important in the following. Okay, and this is what I anticipated before. Okay, and now we arrive to the reason why trees, and this category of trees in particular, are fundamental if we want to encode operads in a functorial way. So there exists a nerve functor, so a functor, from colored operads in topological spaces to contravariant functors from omega to top. And this nerve functor is fully faithful. So we have an embedding. We really can see colored operads in top as a subcategory of this functor category. And like, yeah?
Yeah, sorry, but maybe you're going to say, can we then describe the essential image?
Yes.
Okay.
We are going to do it because it's fun. Yeah, it would be fundamental to understand first of all which functors are really operads, and then if we want to do homotopy theory, it would be interesting to see. Okay, this is the essential image. What if we weaken the defining condition? So how we define this? How do we define this nerve? First of all, well. Okay, suppose for simplicity that P has one color, so we don't bother about colors. So eta, which is just the edge, is going to be sent to the point because there is only one color, so there is only one way to label every edge. And then an M corolla will be sent to Pn, okay, the space of any operations. And then whenever a tree T, oh sorry, here I anticipated, but here there should be whenever a tree T is the grafting of two trees, one on top of the other. Right? Well, what is the value of the nerve of P over T? Well, in P there is no other information that the spaces of operations. So we will define the nerve of P of T as the product of the nerve of P of R and the nerve of P of S. And in this example, well, in this example, for example, the nerve of P of T would be the nerve of P of this three corolla times the nerve of P of these two corolla. But then this is going to be P3 times P2. So at the very end, everything will be determined by the collection of operations, of the spaces of operations of P. Okay, we define this on objects. What do we define on colors? How do we define this on morphisms? Okay, isomorphisms will be related to the symmetric group action that we have on the spaces of operations. The generalizes will be linked. So recall that the nerve of P will be contravariant on omega. So the generalizes will be linked to will be linked to insertion of the identity, basically. But then the most important thing is the action on interfaces. The action on interfaces will represent composition for the tree, for the functor nerve of P. Meaning that, well, this is an interface, so it's a contraction of an inner edge, but on the other direction. Okay, so we should have a morphism from P2 times P2 to P3, because we define this in this way, and we have it because P has the structure of an operad, so we can really embed this with its composition maps. Finally, we also needed, I was sloppy, but not really. And okay, and then finally we need action on outer faces, and the action on outer faces would just be the projection, okay? Because outer faces are inclusions of subtrees, so we will project. Attention, here we really exploited that the tensor product in top is Cartesian, so we have projections available. Okay, so we can now characterize the essential image, the essential image of the nerve functor. What do I mean by essential image? Well, a functor X from omega up to top is the nerve of an operad, so it's isomorphic to the nerve of an operad if and only if X eta is discrete, so X eta is the space of colors, and we started with a set, so it should be discrete. And then for any tree T which writes as the grafting again of two subtrees, the natural map from Xt to this pullback should be an isomorphism. And this is precisely what we saw here. Yeah, okay.
So we have a pullback here, not a product, because now I have colors.
Exactly, yeah. For uncolored, yes, thank you.
Yeah.
For uncolored operad, X eta will be a point, and then this pullback will just be pullback on the point and then a product. So the point here is that this map is induced by the functor, by the fact that X is a functor on omega, and then yeah, I mean, is it? Yes. So it's really induced by the fact that whenever T writes as are grafted onto S, we really have these two maps. And so by contravariance, we will have XC into XR, XC into XS, so by universal property of the product, XC, and onto, suppose it's uncolored, to XS. And this is by universal property of the product, and this is meaningful because it was precisely the tensor product of top. So, okay. Okay, yeah. Why it is useful to having embedded operads into functors? Well, we kind of have linearized the problem, so all of these algebraic relations just become functoriality on the category omega. So this is already nice because as long as you have a functor, you know that it will be associative with respect to these partial compositions. But then, most importantly, it is essential if one wants to do homotopy theory, so the theory of infinity operads. And maybe for this first part, I will stop here. So